Hi guys, in my previous concept I discussed about projectile motion, but projectile flight parallel to horizontal from certain height. So we derived some interesting concepts, the equation of trajectory. So this trajectory we came to know it's a parabola. So that equation we got it y equal to as kx square. Here k is a constant. So y equal to the k value g upon 2u square times x square. After that, we derive an expression for time of flight. Time of flight means it's the total time for the projectile to remains its flight, means the time taken from here to there, starting point, ending point. Now the time of flight t equal to, we derived that square root of 2h upon g. So the time of flight is height dependent factor. Even though g is acceleration due to gravity is constant. So if I rewrite this expression by taking square, so time of flight t equal to under root of 2h upon g. Suppose if I do square on both sides, t square equal to 2h upon g. So the time of flight is square of time of flight is directly proportional to h. It means if we change the height, the time of flight of the projectile is changes. And if we can change from furthermore, so it takes, the height is directly proportional to time, so it takes a longer duration of time. So that time of flight is affecting factor of height. Height is affecting factor in the time of flight of the projectile motion. Now after that, we define the horizontal range. It's a horizontal range, or the maximum distance, horizontal distance the projectile will travel. So this is known as horizontal range, the maximum distance a projectile covered. Suppose if you fired a projectile with initial velocity, so how much maximum distance it covers. Now the time of flight is also depends on the time of flight, the horizontal range r equal to u equal to square root of 2h upon g. So here the range is also depending on the height. Suppose if I do again squaring on both sides, r square equal to u square times 2h upon g. If I can write r square, range square is directly proportional to height. So what does it mean says? It says if we can change the height, the range, the horizontal distance covered by the projectile will change. Suppose if I alter the height at here, now instead of taking 10 meters, if I take 5 meters, to the same initial velocity here 15 meter per second of a football, so or let me take a car, so a car of mass 200 kg. Now if I launch the car, now what is the horizontal distance covered by the car? So here I have, it is 15.5 meter. I wish I'll do it again. So if you can launch a car from a height of 4 meters, so what is the horizontal distance covered by the car? It is the 15.5 meters. Suppose if I change the height, now I am going to launch from the meters of 10 meters. Now in this case, since height has changed, the horizontal distance covered by the car, and this time it went up to 22.8 meters. So in this case, the horizontal range is effects on height. Suppose if we take furthermore one more case, the same initial velocity. Now the horizontal range which is covered by the car is 26.7. Since the formula is depends on the height factor, the range are equal to u times under root of 2h upon g. So if we change height, the projectile horizontal range changes. Not only here, suppose if we change, let me take again 5 meters, the initial velocity. So from this expression, if you can notice, the horizontal range is directly proportional to initial velocity. So if we change initial velocity, instead of taking 15 meters, let me take 5 meters per second. So if projectile is launching, a car of mass 200 kg is launching with the initial speed 5 meters per second from a height 5 meters. So how the horizontal range? Oops. The horizontal range here, it is very less. So it is just 5.4 meters. Now let me take the initial speed of launch. So if it is 10 meters per second, now let me launch again. Now this time the horizontal range has increased. Now in this case it went up to 10.7 meters. Let me increase furthermore. Let me take 15 meters per second. If you projectile launch at a height, I think you are noticing how this horizontal range is depends on the initial velocity, because horizontal range is directly proportional to initial velocity. So different initial velocities gives different horizontal range of the projectile. And every time, if we can notice again to this case, how the vertical component of velocity is changing. In this situation, in this type of projectile, you need to much concentrate only the vertical component of velocity. The vertical component of velocity is changing always, but the horizontal component of velocity, suppose here you can say, oops, let me clear. So if we can, so this is the initial case, the car is going to launch. It do not have any vertical component. So this is horizontal component of velocity and this is vertical component of velocity. If I launch projectile, so I wish I will do that first again. If you launch, how this vertical component of velocity is changing. Now here you can see the vertical component of velocity, that is the key observations we need to do it here. The vertical component of velocity and the horizontal component of velocity. And if I take another location, another position in the projectile, now in this case, if you notice, the vertical component of velocity is increased. So due to all these reasons, all this, how this horizontal range is changing for every time. So that is the responsible component at here, the vertical component of velocity. The horizontal component of velocity is always remains constant throughout the projectile motion. Now apart of that, I derived another thing, the velocity of the projectile at any instant. So we derived that velocity of the projectile by using a calculation. We can do it. Velocity v equal to square root of u square plus g square t square. So this is the expression we got it. Here the t equal to time of flight and g is equal to acceleration to gravity and u equal to initial velocity of the object. If you remember, if any of this projectile, the equation for time of flight t equal to square root of 2h upon g, and horizontal range r equal to u times square root of 2h upon g, and velocity v equal to square root of u square plus g square t square. So all these things what we calculate in the projectile motion are independent of mass. They are not mass dependent, they are independent of mass. These all time of flight, range, and the velocity of the projectile, these all are independent of mass. Suppose here I am having an option, that option gives to me to change the object. So here I projected a car. Suppose if I take a bigger than that, a small object, here the biggest thing is only the car. Suppose if you take a piano of the 400 kg. If you launch a piano, so it's at the same initial speed and the piano reaches to the same horizontal range as like car, because the horizontal range do not have the component of mass. Suppose if you change to smaller object, if you take a human of 70 kg. Now let's launch a human of 70 kg. So the same horizontal range, it's also comes to the same horizontal range, because the horizontal range or time of flight or initial velocity of the projectile is independent of the mass. So let me take finally one small or a golf ball, a golf ball of 0.05 kg or 50 grams. Suppose if you launch a golf ball, so that ball, the smallest ball, also reaches to the same horizontal range. So these are the observations we made for a given projectile motion from launching certain height. So what happens if we change the scenario? It means, suppose there is no height at all. Now I am going to launch the projectile horizontally, but with making an angle. So this is the important case what we are going to study. So the height of launching here goes to 0. So this is the case I am going to discuss right now. The projectile fired at an angle theta with the horizontal. Projectile fired at an angle theta with the horizontal. So here there is no height, just a projectile. We are going to fire at an angle theta. Here you can take that angle, here that the least angle here I can take 25 degree. Suppose in this case if you are launching a projectile, first let us do certain observation. Here the observations what we need to do, the same thing, the component of velocities of the projectile. So here I take velocity and its components. If I launch with a 15 meter per second initial velocity, I don't know how far it go. And if I take a human and if I neglect the air resistance, suppose if I launch the projectile, if you can see clearly at here, so the range, the horizontal range in this situation equal to 17.6 meters. Okay, now let us observe again more carefully how the velocity component is changing. So in that case, if we take the zoom in, now if we try to observe the velocity component, now if you can play, yeah, So here I don't have the option slow motion. Yeah, I'm playing the slow motion only. Yeah. Now do you notice something is peculiar change in the vertical component of velocity. So the vertical component of velocity, so in the initial case, initially, since here you compare this as a coordinate system, x and y axis, so this is y axis and this is x axis. Since we already launching with initial velocity u, so this is initial velocity u equal to 15 meter per second. So in this two dimension, the initial velocity is resolved into two components, that equal to, if it's making along the horizontal 25 degrees, so ux horizontal component equal to u cos theta. So in this case I can write that ux equal to u cos 25 degree. Similarly, the vertical component u suffix y equal to u sin theta. So this is how the velocities resolves in two dimensions. And in this case, velocity vertical component u suffix y equal to u sin 25 degree. Okay, this magnitude we can calculate, that's not big deal. But in this two-dimensional plane motion, projectile motion, the vertical component of velocity, is changing indifferently. So let us try to observe that more carefully. Suppose if I launch projectile more again, this time I will take that initial velocity as 10 meter per second, so that I can get the close up, the horizontal range. Now it's ready to launch. I think you can observe that how the vertical component is changing. So the vertical component is changing. Initially it is increasing, then after at a certain location it is becoming 0, then after it is decreasing. Now if we can do it again at here, I think this will give a good visualization. So I am launching a projectile with an angle of 40 degree with initial speed 15 meters per second. Now this case we can observe. So this is the vertical component and the horizontal component. So horizontal component, this is a u suffix x and it is a u suffix y, horizontal component. Sorry, it is already launched, so its velocity will be changes. So initial velocity changes. Now here we need to take the final velocity, vx and vy. In the initial velocity only here we need to take, where before the launching. Now if I play it again, how the velocity component is changed. Now if I change another location, so this is another point in the projectile motion, so this is a point A and this is a point B. Now here the vertical component is decreased, v suffix y is decreased, but the horizontal component v suffix x remains constant. Let me take one more position. Yeah, yet here it is already decreased. No, it is changed direction. Now the horizontal component remains the same, but the vertical component here it is changed direction. So this is the v suffix y. Now if I continue to play again, now again at here the vertical component. So here the vertical component v suffix y, again it is increased. So till the end. So till the end of the projectile motion, the vertical component is changing a lot. Initially it has both horizontal component and vertical component. So if you can draw at here in free space, so this is the projectile motion. So initially it's have both horizontal component and vertical component. So throughout the projectile motion, so this horizontal component remains the same. Throughout the projectile motion, this horizontal component remains the same. But the vertical component, so here the vertical component is maximum. When it reaches to it here, again it will decreases. At this highest point, the vertical component equal to 0. So V suffix y at the highest point equal to 0. So that's the reason. So it is making a parabola shape. So here from the starting to till this end, the vertical component value decreases, and after becoming 0 again it starts to increases. And this is how the vertical component of velocity is changing in this projectile motion when we launch at an angle of theta. So I wish you do that observation more carefully one more time. So if I launch again, if I can clear this at here, so I like to take car. So let's launch a car with initial speed 15 meters per second. Sorry, I will take that with initial. Now the car is ready to launch. You observe this is the vertical component of velocity of the car, and this is the horizontal component of velocity of the car. Here the arrow marks are little, the green arrows are little less too visible, but try to catch that. Now if I launch the projectile, now this is the point, and you can just keep eye on that vertical component. Again I am going to play that. Now in this point, again the vertical component of the velocity is decreased in magnitude but not in the direction. But at here, at the highest point, the horizontal component is same, but the vertical component of velocity is decreased. At here almost to 0, and again now the vertical component of velocity changes the direction. Now it is going to increase, and it is increasing until then again it reaches to the same. Now here if you notice at here, so the green spot is there. So at this spot the vertical component of velocity V suffix y at there equal to 0. So this is the maximum height point. But throughout the projectile motion, the horizontal component remains constant. The horizontal component is equal to remains constant, but the vertical component, yeah, that is the changing factor. Here that value goes to 0. So vertical component at here goes to 0, but when it comes to other side, so it's increasing again and it increases. So because of the change in the vertical component of velocity, so that change happens because of what? The change is taking place because of one and only factor at here, that is nothing but acceleration due to gravity. The acceleration due to gravity is the cause at here. So I'm going to derive again the same things. What is this trajectory so called? So we call that parabola. So now it is a full parabola. Now that expression gets changes, but still it's called a parabola. Then after we calculate the time of flight and the horizontal range, and this time I'm going to figure out one more thing, the maximum height. So these things we are going to calculate by using the same equations of motions in the 2 dimensions. So that I will make in another video lecture.